the part of the argument that I did last time, just because it is a little bit subtle and we went through it pretty quickly. I want to make sure everybody gets the idea, and then we'll finish up the proof of the greatest common divisor theorem. Okay, so it says let A and B be integers. There exists a common divisor D of A and B with the following properties. Number one, and in some sense the most important part of this, is that D equals MA plus NB, where M and N are integers. Okay, so again, that another way to say that is that it states that this divisor is a linear combination of A and B, but of course when you say linear combination you mean that the coefficients M and N are in Z. These are integers. And the next one is that D is bigger than or equal to 0. We'll see that's not a big deal. And the next one is that if C is a common divisor of A and B, then C divides the greatest common divisor. And now for number 4, actually, Mr. Sunkus pointed out something that I haven't noticed in years of doing this, and nobody else noticed this. We have to be a little bit careful. You have to have that A and B are not equal to 0, not both 0, in order for this to be correct. So, and I'll explain why in just a second. If A and B are non-zero, then if C is a common divisor of A and B, then excuse me, C is less than or equal to D. Okay, so, and the little part about them both being non-zero isn't actually in the text. And often this is stated with just assuming A and B aren't 0 to begin with, but we might as well throw it in there, but we have to be careful with the last statement. So why do we need that? Now that you know we need that, can anybody tell me why we need that? It's kind of a little subtle point. What are the divisors of 0? And? And? Anything. So what are the common divisors of 0 and 0? Everything. So there is not going to be a greatest common divisor because everything divides both of them. But if at least one of them is non-zero, then since 0 only divides 0, then the non-zero one is going to be the greatest common divisor, so everything is fine. Okay, but if they're both 0, not that you ever hit that situation in, when you're actually dealing with these things, but if they're both 0, then everything divides both of them. And actually, number 3 is still okay, right? Because it just asserts that there exists some divisor. And so if they're both 0, what is the divisor, the common divisor that satisfies everything except number 4? How about 0? Right? It doesn't, right? This just says there is one with this property, okay? So there is one that, namely 0, that everything divides, because everything divides 0, but it can't possibly be the biggest one because, in fact, everything divides 0. Okay, so that's mainly the point why we need to add this here, but only to the last statement. Okay, so let's go back and work on the proof of number 1 again. I'm just going to redo it fairly quickly, but give you a chance to ask any questions about it. And there's a lot of little stuff to take care of, right? And so the meat of the proof is the inductive step, right? So we're interested in doing strong induction on K equal to A plus B. And the inductive step because remember we got rid of the 0 case early on, right? So involves, and then it doesn't matter, I mean, we can pick either A or B to be bigger than or equal to the other one, right? And so we had then 1 less than or equal to A less than or equal to B. Okay, so up until that, it was just basically dealing with 0 and other unpleasant stuff that's totally uninteresting, right? So the interesting part of this proof is this inductive step. And so again, what are we assuming? We are assuming this statement here, when A plus B equals K, and then we need to prove it. Well, actually, we're doing strong induction, right? So J for any J between 0 and K. And we're proving it for A plus B equals K plus 1. All right, so I want to just take a minute just to think about this again and remind you of what we're doing, why we're doing this, okay? I mean, first of all, the why we're doing it, this is one of these situations where we're doing it because it works. And that's when mathematics gets more difficult and more subtle, right? Because a lot of the proofs that you do in here, you kind of, I mean, a lot of people refer to it as sort of follow your nose, right? That is, you're at a stage and there's not a whole lot you can do but write out the definition of this or look for theorems that, have the hypothesis being what it is, what step you're at, that kind of thing, okay? Here, you have to try to figure out how to make this work, okay? So what does that mean exactly? Well, and again, this is not something that, I would spring on you cold on the test, right? Because this involves a little experience for how to work with induction. So we're in this situation here, right? We have A plus B equal K plus 1, right? How are we going to use this strong induction, which means we're allowed to use this as long as the sum of the two numbers in question is at most K. It can be anything up to K, but it has to be smaller, right, than K plus 1. So there's really only one way to do that, and that is to replace these two numbers by two new ones that add up to something smaller. But we can't just pick numbers at random, right? Because that's not going to allow us to do anything. And so the idea is that you know all these things by now about how divisibility works. The most important one being that if you have a common divisor of two numbers, this is one of your homework exercises that I hope you've been working on by now, right? If you have a common divisor of two numbers, then that divisor also divides any linear combination of them, right? If D divides A and D divides B, then D divides, AR plus BS, where BS, hope you don't think that's what this is about, where R and S are integers, okay? So what we're going to do is we're going to figure out a way to get our new numbers from A and B, but in such a way that we can reduce their sum. And the way to do that is to let C be equal to B minus A. And why is this going to work? Well, the important thing about this thing in terms of proving that we have a common divisor with this form is what's another way to say how is C being written in terms of B and A?
1 plus negative 1 times A.
In other words, it's a linear combination of A and B. And that's the key here, right? We found a linear combination of these two, and